Part 2, building at scale data, distributed systems, and performance.
Moving beyond the single machine now?
Exactly. This next section focuses on the monumental challenges of building systems that span many, many machines. Modern applications, and especially AI systems, are just defined by their relationship with vast, distributed, and constantly moving data. Our first deep dive here is into Martin Kleppmann's Designing Data-Intensive Applications, or DDIA. It's widely considered the guide to data systems.
Yeah, it's become a modern classic, essential reading.
It really deconstructs the architecture of things like databases, caches, message queues, focusing on those fundamental trade-offs you always face around reliability, scalability, and maintainability.
And when we connect this to the bigger picture, AI and ML systems are, well, they're the quintessential data-intensive applications, aren't they?
Absolutely. The scale is enormous.
They process these huge data sets for training. They need to access low latency feature stores for real-time inference. They manage complex data flow through MLOps, pipelines, machine learning operations.
Right.
DDIA gives you the architectural vocabulary, the mental models to design these systems robustly. Think about concepts like replication and partitioning for scaling training data across many machines, or understanding different consistency models, how data updates are viewed across a distributed system when you're tracking ML experiments reliably.
But I hear this prevalent myth, oh, this book is kind of obsolete now because of serverless platforms and managed data services. The argument is, the cloud handles all these complexities for you. How would you respond to that?
That's a really dangerous oversimplification. These services, they don't abstract away the fundamental principles and the trade-offs of distributed data systems.
They just give you different building blocks.
Exactly. A managed database still has a consistency model, like eventual consistency, where data might take some time to propagate everywhere. An engineer flying blind won't understand why their supposedly infinitely scalable database suddenly grinds to a halt.
Yeah.
Maybe it's because of a hot partition, where too much data or too many requests are hitting a single segment of that distributed database. DDIA teaches the timeless principles that govern all these tools, managed or not. It empowers you to be an intelligent architect, not just a consumer of services.
So how would you apply it?
Okay, imagine designing a real-time feature store for an ML model. You might prompt an AI for architecture ideas, Redis, Cassandra, maybe Postgres. Fine. But using DDIA's mental models, you evaluate them not just as brand names, but as implementations of underlying principles. Redis offers great low latency, okay? But what are its trade-offs for durability if a server crashes? What about consistency? Cassandra gives you high availability, fantastic, but is eventual consistency acceptable for your critical features? The AI generates the what, the options, but DDIA provides the why and the framework for choosing.
Reading DDIA really accelerates your transition then, from maybe a back-end developer to a true systems architect.
I think so.
In an AI-driven world, this means being able to design planet-scale, real-time data infrastructure, not just, training a model in a Jupyter notebook somewhere.
Right, moving beyond the lab.
This expertise is immensely valuable and incredibly difficult to automate. An AI can generate components, sure, but it cannot perform that holistic, trade-off-driven reasoning required to design a complex, distributed system from the ground up.
That's the human architect's role.
Next, we look at software engineering at Google by Titus Winters, Tom Manschreck, and Hiram Wright. This offers a unique look into how Google approaches software engineering. They define it as programming integrated over time.
I love that definition. It emphasizes the long view.
It's about managing the challenges of building and maintaining a massive unified code base that's expected to last for decades.
And the enduring value of this book is its focus on exactly that. Long-term software sustainability at unprecedented scale. This is a problem that AI-generated code will inevitably exacerbate, not solve.
How so?
Well, AI dramatically increases the sheer volume of code, but it offers no inherent solutions for managing the resulting complexity over time. The principles in the Google book, like emphasizing rigorous code quality, comprehensive testing, static analysis, they become absolutely non-negotiable when you start integrating AI-generated code into your systems.
Right.
And concepts like Hiram's law.
Which states?
It basically says that with a sufficient number of users, every observable behavior of your system will be depended on by someone. This becomes critical as engineers start relying on AI-generated code that calls various libraries. If the AI subtly changes some behavior, even an undocumented one, it can break unforeseen dependencies downstream.
Ooh, scary. But I hear the misconception. These practices, they only apply at Google's massive scale. Is that fair?
Not really. The principles are universal. Problems of time and scale affect any project aiming to last more than a few months.
And what about the AI will solve this myth? How does that stack up here? Managing code bases over time.
It's quite naive, actually. AI can generate code snippets, sure, but it cannot manage a complex CI/CD pipeline. It can't design a fair and effective code review process. It can't decide on a sensible deprecation policy for an entire system.
These are socio-technical problems.
Exactly. They require human judgment, long-term perspective, negotiation, communication. Practically, this book gives you a blueprint for integrating AI tools responsibly. If your team starts using AI and maybe consistency or quality starts to drop, you can apply Google's principles. You might institute something like the Beyoncé rule.
The Beyoncé rule.
Yeah, the idea is that any AI-generated code, like Beyoncé, needs to put a ring on it, meaning it needs comprehensive unit and integration tests before it gets committed to the main branch.
I like that. Tests are the commitment.
Exactly. And code reviews must also focus strongly on style, simplicity, maintainability. You could use AI-powered static analysis tools to shift left, catching potential issues earlier in the development process, ideally even before a code review.
Understanding these principles really positions you as an engineering leader, doesn't it?
It does.
The most valuable engineers will be those who can think about the entire software lifecycle, from inception right through to maintenance over decades.
Yeah, the whole picture.
This book gives you the frameworks to lead those crucial conversations about technical debt, testing strategy, engineering productivity. It provides a clear path to leadership roles focused on building enduring systems and effective engineering cultures. That's a responsibility AI is nowhere near capable of assuming.
Not even close. It requires deep human insight.
Okay, our next deep dive is into site reliability engineering, how Google runs production systems, often just called the SRE Book, by Betsy Beyer, Chris Jones, Jennifer Petoff, and Niall Richard Murphy.
Another foundational Google text.
It outlines SRE, this discipline pioneered at Google that treats operations as a software engineering problem, applying development principles to running highly reliable systems.
And this raises an important question. Why is SRE more critical than ever now with AI?
Yeah, why?
As AI models become integral parts of user-facing products, the reliability stops being just a technical concern. It becomes a critical business requirement. Downtime or bad predictions can be disastrous.
Right.
SRE provides a proven methodology for managing these complex, often probabilistic AI systems in production. It offers nuanced approaches like service-level objectives, or SLOs.
Defining measurable reliability targets.
Exactly. And error budgets, which quantify how much unreliability is acceptable. These help you balance pushing out new model improvements with maintaining production stability. For example, you might define an SLO for inference latency, say 99% of requests served under 100 milliseconds, or maybe for prediction accuracy, 95% correctness over a given period. Right. SRE also emphasizes relentlessly automating toil, those manual, repetitive, automatable operational tasks in MLOps pipelines, and fostering blame-free postmortems when AI systems inevitably fail, so the focus is on learning and improving, not pointing fingers.
I sometimes hear people say, oh, SRE is just DevOps with a fancy name, or it's only for massive companies like Google. And then others claim AI will just automate operations anyway. What's your take on those?
Well, while SRE and DevOps definitely share goals, SRE is much more prescriptive and data-driven in its approach. As for AI automating operations, AI can be an incredibly powerful tool for SREs.
How so?
Especially for things like anomaly detection and monitoring data. But it doesn't replace the human judgment needed to define meaningful SLOs in the first place, or to negotiate error budgets with product teams based on business needs, or to design resilient system architectures from first principles. Those require human insight and trade-off analysis.
So how does it work day to day?
Imagine you're managing a production ML service. You'd define measurable SLOs beyond just simple uptime. Maybe that 99% of inference requests are under 100 meters, or 95% model accuracy is maintained. You establish an error budget, the acceptable amount of unreliability for that SLO. Then you use monitoring tools, maybe AI-powered AIOps platforms, to track the service-level indicators, or SLIs. Those are the actual metrics measuring adherence to your SLOs.
Got it.
Now, If a new model deployment causes a rapid burn down of your error budget, an automated system, guided by your SRE principles, could trigger an automatic rollback to the previous stable version, minimizing user impact.
That makes sense. Automation guided by principles.
Exactly. As companies deploy AI in more mission-critical systems, the demand for engineers who can ensure reliability is going to explode. Expertise in SRE is the direct path to filling that need.
It transforms you into a systems engineer who can build and run innovative but also dependable services. You can lead MLOps initiatives, bridge that often difficult gap between data scientists and infrastructure teams,
That's a huge one.
and drive real business value by making data-driven decisions that carefully balance innovation with reliability.
That balance is key.
Okay, to wrap up this section, we're looking at a truly seminal collection of essays from way back in 1975, The Mythical Man-Month by Frederick Brooks, Jr.
A cornerstone of software engineering literature, still relevant.
Absolutely. Its most famous thesis is Brooks's law. Adding manpower to a late software project makes it later. It explores the inherent complexities of large-scale software projects, rooted in things like communication overhead and the need for conceptual integrity.
What's truly fascinating here is its profound relevance despite predating AI by decades. The book isn't really about specific technologies. It's about the human-centric challenges of collaborative creation.
And AI doesn't eliminate those.
No, it just reshapes them. Brooks's famous formula showing the quadratic growth of communication paths as team size increases, that's a timeless warning. And now it's potentially complicated by the idea of AI agents acting as team members, adding new complex communication channels we need to manage. And his argument for conceptual integrity in design, having a single coherent vision, that's a powerful counterargument to just building systems from a patchwork of disparate AI-generated snippets. It reinforces the absolute need for a strong human architect to provide coherence and vision.
The common misconception, though, is that it's outdated because it predates modern agile development or AI.
Yeah.
But isn't that missing the forest for the trees?
Completely. Its insights are about the fundamental nature of software development and human collaboration. Agile methodologies, in fact, are largely a response to the very problems Brooks identified back then.
Right.
And the idea that AI is somehow the silver bullet that Brooks famously said doesn't exist, that's a powerful modern myth we need to be wary of. AI is a powerful tool, a lead bullet maybe, but it doesn't eliminate the hard work of design, integration, testing, validation, especially for large, complex systems. Those remain fundamentally human tasks.
So how does this apply in daily engineering?
Okay, imagine a project is behind schedule. The default management instinct is often throw more people at it.
Classic reaction.
But a leader who's internalized Brooks resists this instinct. They recognize the added ramp-up time, the increased communication overhead. Instead, they might reevaluate the schedule realistically. They'd ensure the core architectural team remains small and focused on those conceptually difficult, indivisible problems. And then they might leverage AI strategically, maybe, to aggressively automate accidental complexity like generating unit tests or documentation, freeing up the human engineers for the essential design problems only they can solve.
Understanding these principles provides a real strategic advantage in project and engineering management.
Immense advantage.
It grounds you in the sober realities of what makes software projects succeed or fail. You can make better planning and staffing decisions, you can champion architectural integrity, and you can provide realistic leadership to non-technical stakeholders, building huge credibility.
Yeah.
As AI changes how code is written, the fundamental challenges of organizing human effort to build large systems, those remain, making this a timeless leadership skill.
Absolutely. It's about managing complexity, both technical and human.